Hey, alright. Here we go. So we only got a few folks here at the moment, so I figure I'll let the go live notification go out and see if we don't pick up another few people. Do y'all have any questions before we get started? About any of the usual sorts of stuff? I do want to mention again, I sent that email out, but this is a word problem section, so I put up a worksheet of applied optimization word problems up on Canvas, if that might make it easier to follow along rather than having to write out all of the word problems again. Yes, this is the homework and quiz that are up, are the last homework and quiz. On Friday afternoon, I'll hand out the final exam. And the class on Monday will just be whatever questions folks have. As will the class on Friday, but it'll be more of a review thing rather than questions about the exam, because you won't have the exam yet. Any other questions before we get started? So, those are due at the end of the semester. They have a due date with them. You were supposed to have done them the first couple weeks of class. I know that almost no one has done them, but that's when you were supposed to do them. They have due dates posted with them. I don't remember what they are. But those weren't homework and quizzes. Those were something to make sure that you were in the appropriate class. Alrighty. Well, if anybody else has any questions, go ahead and throw them up there. And we'll go ahead and get started with our little recap. Okay, that certainly sounds like we're better. Alrighty, sorry about that, folks. So, when we want to do this whole applied optimization thing, first we're going to need to find a couple things. One is what the book calls the objective function, right? So that's going to be the thing that we either want to maximize or minimize. And then we also want to find the constraints. So that tells us some restriction on the variables. So it's usually, not always, an interval. Right? That's one of the things we talked about way back with the first time when we talked about finding extrema, is that if we have a closed interval, then we are guaranteed to have an extrema. Both types of extrema. If we don't have a closed interval, then we might have one or we might not. So we'll deal with some of those things. And once we have all that, then we need to find the critical points of the objective function. Right, and lastly, we need to plug in the critical points, definitely. The endpoints, if we have them. And one of the other things we might need to do if we don't have a closed interval is find the limit as x goes to the non-included endpoints of f of x, right? So if we're going off to infinity, if we don't have any constraints on our function at all, then we might need to take the limit as x goes to infinity. If we've got an open interval, then we might need to take the limit as we go to the endpoints. But this last one is sort of a special case. And so there's not, yeah, it got bad. Let's see if I can make this look better. Yeah, it's still pretty small. Okay. So we don't have any new stuff to learn how to do. We're just putting it together. So we got ourselves a word problem here. It's probably a little bit hard to read on the screen, but this is coming from the worksheet that is up on Canvas. So we're given the monthly output. Right, so I'm going to break this down sort of entirely here for this first one. Alright, so one of the things we always need to do is make sure we know what all of our variables mean. So our output is P, and we've got a function for it. L is the cost of labor, K is the cost of equipment. They need to produce 1.7 million. And we want to minimize L plus K. Right? And so that right there, right, specifically, let me see if I can't come up with some sort of highlighter thing. There we go. That works out. So we have that sentence saying minimize L plus K. So this is our objective function. Right? But we've got a little bit of a problem there, because that's a function of two variables. And we don't know how to find extrema of functions of two variables. So we need to figure out some way to write that either with all L's or all K's. Right? So this is actually involved with finding the constraint. Sometimes finding the constraint helps you finish off finding the objective function. Right? And this statement right here is the thing that's going to give us a constraint. Right? Because we already know a function that has L and K in it. It just also has P in it. So that's not really going to help us figure out what L is in relation to K. But we want our monthly output to be 1.7. Right, so our company needs to produce 1.7 million units per month. Right, so maybe that should have gone here. So this statement here says we need P to equal 1.7. Right? That's a way to translate it into the variables that we have here. Right? Because that's the trick with a word problem, is we need to make sure we understand what the variables mean. And then we need to rewrite all of those words as math statements. Right? So our constraints are going to come from the fact that we want 1.7 to equal 2 times L times K squared. So, now that we have an equation, not a function but an equation that has both L and K in it, we can solve for one of them. So which one do we want to solve for? Which letter do we like better? Alright, well, I'm going to pick K, because that's going to let us discuss more. Alright, so if I want to solve for k, I'm going to divide by the coefficient. And then I'm going to take the square root of both sides. And whenever you take the square root of both sides, one of them needs to have a plus or minus. So we've got a little bit of a problem here because we've got two things that k could be. So we need to think about this in terms of what k is, right? If this were just an algebra problem, then k has two values and we just have to deal with that. But this is a word problem. K means something, right? So do we think it's likely that k is ever going to be a negative number? So what is k? What does k mean in this problem? What is k representing? So what does k represent? So here in this problem, according to, oh gracious, according to this sentence and what we pulled out here, K represents the cost to this company for the equipment in a given month. Right? And usually, costs of equipment isn't negative, right? They're probably not getting paid money for using that equipment. Right? So since K is the cost of equipment, we're just going to go with that positive one, because that cost of equipment is never going to be a negative number. That just doesn't really make sense. Right? So, this here gives us our constraint. Right? So, I'm going to need to do some fiddling here. I'm going to take all of this and move it way down here. Alrighty. So now that we have a constraint, we can plug this in to the thing we want to minimize. And have a function of just one variable. Right, which is the type of thing that we know how to maximize. Right? We do still need an interval for this of some sort, right? It can be everything if it needs to, but we need to go ahead and write that down. But in this case, we're not going to quite be everything in the world forever. Right? Because if we look back up here at the problem, L is the cost of labor. Right? So L is another cost. Which means that while, I don't know, we might have a time where the cost of labor is nothing, we're never going to have a time where the cost of labor in and of itself, by itself, is negative. So our interval is, it can get all the way down to 0, and then it can get up to who knows what. So according to our process up here, now that we have found the objective function and the constraints, our next step is to find the critical points of the objective function. So I'm going to give everybody a little bit of time to wake up some more and remind us that to find the critical points, that's where we take the derivative and find where it doesn't exist and where it's equal to 0. So the first piece is easy to take the derivative of. The derivative of L is just 1. So here, I'm actually going to rewrite this a little way so it's a bit clearer. How I'm getting it. Alright, so we can just use the power rule right off. Alright, so this square root piece is a constant, And then we can use the power rule on this L to the negative 1/2, which says to pull that negative 1/2 down, have another L, and subtract 1 from the power. Right. So that is our function there. And we could rewrite this if we want as just so that we can see how exactly things might be 0 or not exist. So we have our derivative. And if we check where it doesn't exist, that means we're looking where any denominators are equal to 0. And that just means that L has to be 0 in this case. Right? So one of our critical points is one of our endpoints, so that should save us a little time. Right, so our other crit points are going to come where this function equals 0. So we go about solving this. This actually would be handy to use the other form of it, at least in my opinion. So I'm going to write it up that way. So I'm going to go ahead and get that L by itself by multiplying by some reciprocals. All right, just to make it clear where that comes from. And then to get rid of that 1/2, I'm going to square things. Yep. I'd like to get rid of that negative, so I'm going to flip everything over. And maybe I'll go ahead and multiply through just so I don't have to keep writing 2 fractions down. Right. And then lastly, I'm going to take the cube root. Right, so we've got our 2 critical points now. And if we zoom back up, we've got our interval. So that tells us that we need to check out 4 things. All right, we need to, well, 3 really. We need to compare f of 0, both because 0 is an endpoint and a crit point. We need to make this thing go very far away. We need to figure out f of our other critical point. All right, we need to evaluate that. And then lastly, we need to try for the other endpoint. Right? We can't just plug in 0, but we can let x, or we can't just plug in infinity, but we can let x go to infinity. Oops. Ooh, going crazy. Okay. So, I'm going to have to stay zoomed out a little bit here. So we've got a little bit of a problem with that f of 0. Right? Which is that it can't be 0. Right? F of 0 also doesn't exist. Right? So we can't really do that one. And when we plug in this guy, I didn't actually do this ahead of time, so I'll have to bring up a handy dandy calculator. Y'all get to hear my super clicky keyboard. Let's see if Google's able to understand that. Well, certainly seems to be. I'm a little bit suspicious of that number. So I'm going to try it a slightly different way. Okay, no, it seems to understand. So apparently this is roughly 1.31. Right. And then lastly, we have to do this limit. So L goes to infinity as L goes to infinity. And this thing that has L in the denominator goes to 0 as L goes to infinity. So the limit seems to be going to infinity. So that gives us really, let's see, what did we want to do? We wanted to minimize, right? and as I'm pretty sure that 1.31, roughly, is less than infinity, that means that our answer is L equals the cube root of 1.7 over 8. Now the problem, all the way back up here, which, here we go, says what values of L and K would minimize the total cost function, which means we need to figure out what L is. Or what K is, rather. We've already figured out what L is. Right. Again, it's probably hard to see, but I'm using this formula we found up here. Getting that ever so lovely number. So, all this stuff that we went through, do we have any questions about any of the steps that we took? Alrighty. Do we have any problems from the worksheets that we particularly want to do over another? Alrighty. I'm just going to take all of this, shove it down to the end of the page. We'll come back for it when we need it. Alright, I appear to have lost a little bit of this. But I can fill it back in. Alrighty. So, our problem says the law of mass action for chemical reactions gives the following reaction rate. R of x equals k times ax times bx, where 0 is less than or equal to x is less than or equal to the minimum of a and b. We have that k is 65, a is 10, and b is 8. And we want to know the concentration of x where the reaction rate is at a minimum. So, what is our objective function? What is the thing that we are trying to maximize or minimize? So, this final sentence here, the one that actually tells us this is an optimization problem. I mean, the fact that the worksheet starts off with applied optimization really tells us that. But if this were on, say, a final exam, the thing that would tell us this is an applied optimization problem is the question has the word maximum in it. Right? So we know we're going to be wanting to maximize, not minimize. Right? And that sentence says the reaction rate is at a maximum. So the thing in words that we're trying to maximize is the reaction rate. And so if we scan the rest of the word problem for reaction rate, we also find it up here where it's labeling this function r of x, which is kax times bx so that's our reaction rate. That's an awful lot of variables we have there. So how can we simplify this problem? What else do we know about this situation? So we have a whole lot of extra variables in this problem, but they're not actually variables, they're really just constants. Right? And we're specifically told what they are. We're told that k equals 65. We're told that a equals 10. And we're told that b equals 8. So in other words, we get 520 x squared. So this is our objective function. That's the thing that we're trying to maximize. So the other thing we need to do in order to set ourselves up properly is figure out the constraints. Is there some sort of interval of values that we're looking at? And this one got split up in an unfortunate way, but it does directly give us what values x is allowed to be. So our constraints are 0, because 0 is less than or equal to is why we get the square brackets. And so according to the problem in general, it's less than or equal to the minimum of a and b. But for this problem in specific, we know what a and b are. We know that a is 10 and b is 8. So we know that the interval that we're looking at is 0 to 8. So we've got our objective function and we've got our constraints. That was the first step of this process. The second step was finding the critical points. So what do we need to do to find the critical points? So we're either having a bad day all around, or maybe my chat's just broken. But we find critical points by taking the derivative and the I setting it equals 0, figuring out where it doesn't exist. Finding the derivative is easy enough. It's just a simple power rule in this case. Right? We bring this 2 down, multiply it by its coefficient, and then it just has 1 left over. And finding the places where it does not exist is even easier, because there are none of them. Polynomials always exist everywhere. Really, If I was not working this out as an example, I wouldn't even put that, because there's no point in even thinking about it. It's just a polynomial. And if we set the derivative equal to 0, then that's just going to get us x equals 0. So we do have one critical point, but it is at an endpoint. So that's going to make our step 3 really easy. We need to plug in the endpoints. And we need to plug in the critical points, but there's only one, and it's already an endpoint. Let me bring out my handy-dandy calculator again. I think I missed a 0 somewhere. Yeah. That's not actually going to change anything we've done. But I forgot to multiply by the 10 there. Oop. Don't need to make that x big. Yeah. Yeah, I think that's what we got. So, on one hand we have 0, and on the other hand we've got 6 digits. And since what we wanted to do was maximize, then our maximum is definitely that number there with 6 digits. Alright, so since we wanted to figure out the concentration of x, we wanted to figure out what x was, x equals 8 is going to be our final answer. Any questions about any of the steps we did here? Also, again, are there any on the sheet that we'd specifically like to do for our next problem? Let's see. Sure, we'll go ahead and since nobody's asking for one in particular. Alrighty. So, what we have here is find the points, should they exist, on the line y equals x minus 1, closest and farthest from the point 0, 0. Right? So this one is a little bit tricky in that it doesn't have the words minimize or maximize in it. Right? But what it does have are these words closest and farthest. Right? So those are est words. So they're a lot like maximize and minimize. But those are not only telling us that we want to both maximize and minimize, but they also, just in that word by themselves, are telling us what we want to maximize and minimize. And that is, we want to maximize and minimize the distance. Right? If you're finding the closest thing to you, you are minimizing the distance between you and that thing. If you want to find the thing farthest from you, you are maximizing the distance. I have a large word. There we go. You're maximizing the distance between you and that thing. Now, this might be a blast from the past, but the distance function is the square root of the difference between first coordinate squared plus the difference between second coordinate squared. So we've said that one of the points in question is 0, 0. Right, so we can do this. And if we're subtracting 0 from x, we just get x. And if we're subtracting 0 from y, we just get y. Right? So, if all we wanted to do was find a point, the distance from a point to the point 0, 0, this would be our function. Right? But that gives us a similar problem to what we had at the very beginning, where we have here a function of two variables. Right? This is a function of x and of y. And we're in Calculus 1, we don't know how to deal with functions of both x and y. Except in the weird case of implicitly defined functions, and we don't even have that because this isn't an equation. Remember, implicitly defined functions are going to have an equation. So, do we have anything here that relates x and y? Do we have an equation that has both x and y in it? it turns out we in fact do, right? We're not trying to find any point whatsoever that is furthest and closest from 0 to 0. I can go ahead and tell you right now, the closest point to 0, 0 is 0, 0. And there is no point that is maximally far away. But we specifically want points to live on the line y equals x minus 1. Right? We don't care about every point ever. We care about points where this is true, where this is a true relationship between x and y. Right? So the function that we're both maximizing and minimizing is we're going to have that x squared, but we're going to replace this y with something that it's equal to, which is x minus 1. All right, now I'd like to simplify that a little bit. Right. So we get this square root equation once we multiply that out and combine like terms. Now, the other thing we need to check on, right, again, I said usually but not always, we'll have an interval. Right, and this one specifically doesn't. Right, the only real constraint we have is that it has to be on that line. Right, so since that function is a line, we know that x is allowed to be anything. Right, if that was, say, the square root of x minus 1, right, so let's put a thought bubble over here. If we were looking at this, right, well, in this case, x has to be bigger than or equal to 1. Right? So that would give us an interval that's at least half closed, and that might help. Right? But for this function, for y equals x minus 1, there's no restrictions on what x is. Right? So you can either think of it as not having an interval, or that our interval is negative infinity to positive infinity, which is just everything. Right. So we have our constraint. We came up with our objective sorry. We came up with an objective function. So now it's time to find the crib points. And as we've said the past couple times, and as we've said the past couple sections, we find crib points by taking the derivative and figuring out where it doesn't exist, and figuring out where it's equal to 0. So first we need to take that derivative. So this is going to be an instance of the chain rule, right? Because d of x is a polynomial being plugged into the square root of x. Oops. There we go. Now I can see it. Q suddenly came from. Right, so the derivative of the inside is just some power rule stuff. The derivative of the outside is this guy, which is 1 over. So then the chain rule says that we want the derivative of the outside with the inside plugged in times the derivative of the inside. So, I've got a couple of things here to check. First is where it does not exist. And there's two aspects of this function that might cause problems, right? Polynomials exist everywhere, but fractions, rational functions, don't exist where their denominator is equal to 0. So that's one possibility for the not existing. And square roots don't exist where the thing inside of them is negative. Right? But that, if that was going to come up, that should have come up here in the constraints. Right? So one thing we know about this thing that we wrote down here, no matter what x is, if you square it, you get something positive. Right? No matter what x minus 1 is, if you square it, you get something positive. And so if you take two positive numbers and you add them together, you're going to get something positive. Right? So we know that this guy is going to exist no matter what x is. Since this is the exact same square root, just shoved to the bottom of the fraction, the square root's not actually going to cause any problems here. Right, so we just have to figure out this guy, where we divide by 2 and square to get this. And then that is a quadratic equation. It doesn't have a leading coefficient of 1, so I'm inclined to use the quadratic formula for it, right? There's a modification of our trick about two numbers that multiply together to get the constant and add to get the linear, but I really just prefer a quadratic formula when there's not a 1 for the leading coefficient. All right. So we're looking at negative b plus or minus the square root of b squared minus 4 times a times c. Well, and right here I can actually stop because I can see that something's going to go wrong here. Right? Because 4 minus 8 is negative 4. And that negative 4 is underneath the square root, which means there's not going to be any solutions. Right? So whenever you're using the quadratic formula, one of the things you'll really want to pay attention to as you're writing is this thing here, right? Which, if we recall from pre-calculus, is called the determinant, or discriminant, sorry. And if that discriminant is negative, then we know that the equation is not going to have any solutions. So this function never doesn't exist, so that's nice. And since it's a fraction, right, so let me go ahead and get this written down here. Right. If I want that to equal 0, that's the same as taking the denominator and setting it equal to 0. Right, so we get x is equal to 1/2. Right. So our only critical point is x is equal to 1/2. Just gonna make all of that go away. So our last thing is to check. Right, so we only have one critical point. So we need to check that out. Right, and then looking at this interval that we got, or the fact that we don't have an a real interval, however you want to think about it, then we need to think about the limit as x goes to infinity of d of x, and the limit as x goes to negative infinity of d of x. Right. So if we plug in 1/2, we get 1/2 squared plus negative 1/2 squared. Right. Oops. Might help if I zoomed it in a little bit. So we get the square root of 1/2 for that. Oh, that's why I had it up in the first place, so we could see what D was. How far do I have to go? Okay, there we go. We get D right here. Really, that's the D that we want. Right, so if we think of this function up here, right, if we let x go to infinity, then so is x squared. And so is x minus 1. And so is x minus 1 squared. So this guy is going off to infinity. Now, negative infinity, on the other hand, if x is going to negative infinity, then x squared is going to positive infinity. And if x is going to negative infinity, x minus 1 is going to negative infinity. But then again, when we square it, it starts going to positive infinity again. So the square root of positive infinity plus positive infinity is just infinity. So what this tells us is there's no maximum. right? Specifically because these are both positive. Well, really, it's since either one of them was positive. If either one of them had been going to positive infinity, then we'd have no maximum. And the minimum is this guy here, and really that's the one that is since both are positive. Right? So on either side, the function is going off to positive infinity, and so we're never going to ever reach the biggest number, because we're just going to get closer and closer to infinity. Right? But neither of them are going down to negative infinity, so we can actually reach a smallest number. Right? And it's going to be that square root of 1/2. Any questions about anything we've done here? This was another long one. Alrighty, well, I'll see y'all Wednesday for our last section. The last homework is due tomorrow. The last quiz is due Thursday. The final exam is going to go out Friday afternoon. And we're almost at the end of this 12-week semester. I hope everyone is still doing well, and I will see y'all Wednesday.